Great. So, welcome to this class. I'm going to continue from where we left off last week. If you remember, we did linear regression. Then we said, okay, well, we need to review some of our linear algebra, and that's what we did last time. And now I'm going to continue, spend a little bit more time on linear algebra review, and then go back to the problem of regression. So before I start, are there any questions for me? Okay, so we have placed the lecture notes and the video on Canvas. So all of you should have access, and we'll basically keep on uploading them after each lecture. Okay, so let me start. Just reviewing the things that we did last time. So we talked about vectors. Each vector has a norm or a size and a direction. Size is called norms. We talked about different kinds of vector norms. In general, the LP norms. Then we talked about, orthogonal projector onto just one line, which can be generalized to subspaces. Talked a little bit about Cauchy-Schwarz inequality, basically the angles between two vectors. The cosine theta can be written as x transpose y divided by 2 norm of x, 2 norm of y. That's the angle between or the cosine of the angle between the vectors x and y. And then we moved on to talk about matrices. An m by n matrix is a linear transformation from n-dimensional vectors to m-dimensional vectors. Again, matrices have sizes or norms. They're straightforward extensions of vector norms to matrices, where we think of an m by n matrix as an m times n dimensional vector. So from that, we get corresponding LP norms, including the square root of the sum of squares of the absolute value. That's called the Frobenius norm, right? And then similarly, like the sum of absolute values, which corresponds to the L1 vector norm. But then we saw that matrices have other kinds of norms, which are called operator norms, right? So if you think of them as linear transformations, then you can look at how much they change the size of vectors from the domain to the range. So if I take an x and I apply a to it, how big or small is a times x compared to x? And that we can measure in different norms. So if we measure it in 2 norm, then we get the maximum singular value of the matrix A. And similarly, we can get, the one operator norm of a matrix and the infinity operator norm. Matrices have, when there's a non-trivial null space, and I'll talk a little bit about that today, then matrices are singular. So one way to measure the closeness of a matrix to singularity is something called the condition number of a matrix. And that can come into play when you're talking about regression. And I'll probably mention that a little bit later. Then we started talking about, square matrices and some of the properties they have. So when you talk about square matrices, you have the concept of eigenvalues and eigenvectors. The eigenvalues are basically the roots of the characteristic polynomial, which is a polynomial of degree n. And as a result, an n by n matrix has n eigenvalues. In general, even if a matrix is real, then it can have real as well as complex eigenvalues. But then there's a special class of matrices called normal matrices, where all the eigenvalues are guaranteed to be real. And symmetric matrices are a special subclass of normal matrices. So symmetric matrices, which is mostly what we encounter in machine learning when we talk about eigenvalues and the eigenvectors, they are special, the symmetric matrices. The eigenvalues are always real, but not only that, they also have a full set, which is, if a matrix is n by n, the full set is of size n, and they have n mutually orthogonal eigenvectors. And that's definitely not true of all matrices. Okay, so if you are looking at a symmetric matrix, we can actually get what's called the eigenvalue decomposition, because A times V is equal to V times lambda. Lambda is diagonal, V is orthogonal. And this is called the eigenvalue decomposition, but of course it only exists for, this kind of decomposition only exists for, well, normal matrices, in our case, symmetric matrices. There are special classes of subclasses of symmetric matrices where not only are the eigenvalues real, but they're also greater than or equal to 0. Those are called positive semi-definite matrices. Okay. And then towards the end of the last lecture, we talked a little bit about singular value decomposition. Eigenvalue decomposition requires the matrix to be square, and really we talked about the eigenvalue decomposition of a real symmetric matrix. But the singular value decomposition actually exists for all matrices. And there's an interesting saying about the singular value decomposition. When you take a matrix, you can do different kinds of decompositions of it. Eigenvalue decomposition for real symmetric matrix. Then there's the Jordan canonical decomposition. Then you can do LU decomposition from Gaussian elimination. And somebody remarked that the singular value decomposition is like the Rolls-Royce of all matrix decompositions, as well as the Swiss Army knife of all matrix decompositions. So that means that, it's very rich theoretically, and in some sense quite intriguing and beautiful. That's why it's the Rolls-Royce. It's also extremely useful in a lot of computations. And as a result, it's also the Swiss Army knife. So that was a kind of quick recap. And so today, let me start off with the singular value decomposition. And so today I will talk about, sorry, 1 minute. Today I'll talk about SVD, oh, sorry. Today I will talk about SVD and regression. So I will tie up these two different topics. Okay, so let's review what the SVD is. We touched upon this at the end of the last lecture. Okay, it's the singular value decomposition, hence the acronym SVD. Okay, so like I said, it exists for any matrix. So let A be any general matrix, real matrix, M by N. As I kind of said, you don't really get complex matrices in machine learning, so we'll always talk about real matrices. So the SVD, as we discussed last time, is a decomposition where I can express U as equal to U sigma V transpose. And here, what we have is that U and V are orthogonal matrices. What do I mean by orthogonal matrices? I mean that U transpose U is equal to I and V transpose V equals I. There are two ways you can define an SVD. So first we'll define an SVD where U and V are actually square matrices. And because this says that, the inverse of U is U transpose, or the left inverse of U is U transpose, and the matrix is square, the inverse is unique. This means that U transpose is also equal to the identity. Okay? So U transpose U equals U transpose is the identity when U is orthogonal and square. And then you have sigma, which is a real and diagonal matrix. Okay, and actually it's also non-negative. So it's a diagonal matrix with non-negative values on the diagonal. Okay, so let me, for now, let me draw this out. So let me first assume that M is greater than or equal to N. So let me draw an Mn matrix where M is bigger than N. So this is M, N columns, and I have this matrix A. And what the SVD says is that there's a decomposition where I have it equal to U. So this is the matrix U. This is M by M. And then I have a matrix which is, M by N. And that is sigma. Okay. And then my V transpose is N by N. So note that U and V are square matrices. Okay. And I can think about U as having the columns U1, U2, and we'll go up till, let me just make a distinction that there is UN, UN plus 1 to UM. Each of the UI belongs to RM. And then the singular values are, was there a question? Sorry. Okay. If there's a question, just kind of always just interrupt me, because I sometimes don't see the chat. I don't think there's a question, but let me know if there is. Okay. Sorry, I just had heard a beep, so that's why I thought there was a question. Okay, and so the matrix sigma, capital sigma, these are little sigmas, sigma 1, sigma 2, lowercase sigma, sigma n. These values are zeros, and so are these values. Okay, so it's a diagonal matrix. And then I have V1 transpose, V2 transpose, Vn transpose. These are the rows of V transpose or the columns of V. So this matrix U consists of left singular vectors. Okay, so sometimes it's called the matrix of left singular vectors. So maybe it's better if I make the arrow to be pointing from here. Okay, so these vectors U1 through UN plus 1 through UM are called left singular vectors because they appear on the left of the decomposition. So similarly, these are the right singular vectors. Okay, and note that U transpose U equals I. That means that if I take UI transpose UJ, that is equal to 1 if I equal to J, and 0 otherwise. Okay, so that means these vectors are mutually orthogonal. Okay, and they basically form an orthogonal basis for Rm. And since it is square, let me actually explicitly write it because this is important. Since U is square and U transpose U equals I, this implies that U transpose equals I. So what you have is U transpose U equal U transpose equals I. And note this is only because U is square, okay? And we'll come to situations where we might actually encounter orthogonal matrices that are not square, okay? So similarly, V transpose V equals I. Again, it's an orthogonal matrix. Vi transpose Vj is equal to 1 if I equal to j and is 0 if I not equal to j. Okay, and clearly over here, you have I and j are between 1 and n, and over here, I and j are between 1 and m. Okay, and then the all-important singular values. These are the singular values over here. These values. Okay, so let me kind of just say singular values. Typically, they are arranged in decreasing order. So the convention is typically that we'll write it as sigma 1 is greater than or equal to sigma 2 is greater than or equal to sigma n, which is greater than or equal to 0. Okay, so sigma I belongs to R plus. That means they are non-negative numbers. And typically they are arranged in decreasing order. Okay, so that's the singular value decomposition. And let's talk a little bit more about the singular value decomposition. If A is equal to U sigma V transpose, so if I have this decomposition, this means that if I multiply each side, both left-hand side and right-hand side by the matrix V, then I get A times V is equal to U sigma V transpose V. And since I know that V transpose V is the identity, this means that this is equal to U sigma. Okay, so that means that A times V is equal to U times sigma. Okay, you can cast your mind back to this. Not, remember, it's starting to look a little bit like eigenvalue decomposition, but it's different. Okay, because here what we have is A times Vi. If I look at the ith column of both sides, A times Vi is equal to sigma I times Ui. Okay, for 1 is less than equal to I is less than equal to n. Okay, and now notice one thing over here. Okay, I have this matrix A, which is m by n. So in this case, the number of columns is smaller than the number of rows. But this matrix is m by m. This matrix is m by n. If I look at the last m minus n columns of U, and if you think about matrix multiplication, then you'll see that this part gets multiplied by this part. And this part, un plus 1 through um, is actually multiplied by the 0 matrix, this part. And that's actually 0. So really, the way you can write this decomposition is A is equal to the first part of U times the upper part of sigma, and the V is left unchanged in the case that M is greater than or equal to N. So sometimes people will call this the full SVD, okay? And when you have the full SVD, there's something called either the thin or reduced SVD. Okay, and that's the following. Thin or reduced SVD is A is equal to, so that you are clear that this is a different U and sigma, I'll just write it as U hat, sigma hat, V hat transpose. Okay, and in this case, AI, sorry, in this case, U hat belongs to M by M, sorry, M by N. Okay, so U hat is actually rectangular matrix. It's still orthogonal because U hat transpose U hat is the identity. Sigma hat belongs to, this is now a square matrix, N by N. And V hat is also a square matrix. And this is V hat transpose V hat equals identity. Okay, and this is now a square diagonal matrix. And really, I'm not doing anything new. If you know about the full SVD, the thin SVD actually just follows, because what you can do is you can take this part of U, and this is just U hat. Okay, so the M by N matrix with the first N left singular vectors forms U hat. Now, the important thing to realize, and this comes up when you are kind of manipulating formulae around, and that's one of the reasons why I want to stress it, is that in general, if M is not equal to N, right, in general, U hat transpose is not the identity. So I can't just reverse this because U hat is not square. On the other hand, when M is greater than or equal to N and V hat is square, then V hat is square, which means that V hat transpose is the left inverse. When you have a square matrix, the left inverse is the same as the right inverse. As a result, you actually have that V hat transpose is equal to the identity. Okay? Any questions so far? Okay, it's a very important decomposition, and it can come up in different scenarios, and we'll see that there's one particular way of regularizing called for regression, called ridge regression, and we will see that by knowing the SVD, we can actually get a much better and much more interesting interpretation of what ridge regression does.
Question, sorry. So
Yeah, go
what
ahead.
significance of U over the U hat? Because it seems like all those, the other vectors, the greater than N to M, are basically getting to zero by the multiplication. So
Exactly.
yeah, so why are we even care about creating the U rather than U hat?
Yeah, so you'll see that sometimes it'll be easier to use U hat, but I will actually come to a characterization of the entire U. So, when you're doing a first course in linear algebra, you might have studied things like the column space of a matrix, the row space of the matrix, the null space of a matrix, the null space of its transpose. So we'll actually see that the vectors un plus 1 through um, they're actually they form a basis of the right null space of A.
I see.
Okay, so it's just good to carry it around so that, the full singular value decomposition just gives you, a holistic picture of the entire matrix.
Thank you.
And
Yeah,
in many cases, you only need to use the thin SVD.
I see. Thank
Okay.
you.
But whenever you are doing it, you should just make sure that you realize which one you are using. Because like I said, in some cases,
Correct.
UU transpose is equal to identity, and in some other cases, it may not be. And we'll actually see that regression is just doing the operation of UU transpose. It's actually, UU transpose is actually an orthogonal projector, and is actually projecting onto a particular space defined by the matrix of the data with all its features. And again, I'll come to that very soon.
Thank you.
Okay. Okay, so let's do a little bit of like manipulation with SVD. So if I have the SVD of A, and let's use the reduced SVD, A hat is equal to U hat sigma hat V hat transpose. Well, this implies that A transpose, what is A transpose? Well, it is U hat sigma hat V hat transpose. And if you know the rule for, taking the transpose of a product, right? So in general, if you have XY transpose where X and Y are matrices, this is Y transpose X transpose. So as a result, I have V hat transpose, which is V hat, sigma hat transpose, but it's square and symmetric sigma hat. So it'll be the same as sigma hat. And then I have this. Okay. So this is V hat, sigma hat, U hat transpose. So if I do A transpose times A, so A has this as SVD, and the SVD of A transpose is actually over here. Okay, so obviously it's clear that when you have the SVD of A then you actually have the SVD of A hat. Sorry, A transpose. Okay, so A transpose A is equal to V hat sigma hat U hat transpose, right, times U hat sigma hat V hat transpose. Okay, so you'll see that I have U hat transpose U hat over here. This is the identity. So as a result, I have this is V hat sigma hat square times V transpose. V hat transpose. And if you think about it, remember that A transpose A, what is the size of A transpose A? Well, remember A is M by N. So A transpose A is actually N by N.
By M, N by N.
Sorry, did I?
M by N.
Yeah, A is M by N.
Yes.
So A transpose A belongs to N by N. So A transpose A is square matrix. And then what do you see over here? Well, you actually have the eigenvalue decomposition. Of A transpose A. So you can actually look at this and realize that the singular values are basically square roots of the eigenvalue. The singular values of A are the square roots of the eigenvalues of A transpose. Okay. Similarly, if I do A transpose, then I get U hat, sigma hat, V hat transpose, V hat, sigma hat, U hat transpose. V hat times V is identity. And so I get U hat sigma hat square U hat transpose. And what is that? That's again now the eigenvalue decomposition, right, of A transpose. So given A, you can see that A transpose A and A transpose A and A transpose are actually kind of linked together. They have the same eigenvalues, but their eigenvectors are different, right? A transpose A has eigenvectors V hat, and A transpose has eigenvectors as U hat. Okay. And you can say also, remember that we talked about positive definite matrices. A transpose A and A transpose are positive semi-definite matrices. Okay, and that becomes clear from here, right? Because there's a square over here. Okay, so that means their eigenvalues are greater than or equal to 0. Okay, so that's when I said, the singular value decomposition is the Rolls-Royce of all matrix decompositions. This is one example, right? It has very kind of interesting properties, right? That A transpose and A transpose A are really linked together through the SVD. Now let's look at even a more really beautiful part of the SVD, right? So remember that let's think of M is greater than or equal to N. A belongs to M by N, okay? And let me now write the SVD, okay? A is equal to U sigma V transpose. I have A transpose is equal to V sigma transpose U transpose. Sorry, not sigma hat. So here, by the way, I'm doing the full SVD, okay? So U is square and V is square, and sigma is actually rectangular. Now, in both cases, I can take A times V is equal to U times sigma. Similarly, I can take A transpose times U by post multiplying both sides by matrix U. I have V sigma transpose. And this means that A, if I look at each column, A of Vi is equal to Ui sigma I for I between 1 and n. And similarly, I have A transpose Ui is equal to, well, here actually I need to be a little bit careful, right? A transpose V Ui is equal to Vi sigma I for I between 1 and n. Because there are only n V's. And then for the rest, A transpose Ui equals 0. Okay? N plus 1 is less than or equal to I is less than or equal to n. Remember, I talked about the SVD as, a matrix as doing a linear transformation. So if I have an M by N matrix, A basically is a map, linear map, represents a linear map, linear transformation for Rn to Rm. So this is x to A times x. Now what is A? If I know the SVD of A, this is U sigma V transpose times x. So now I can break A times x into three parts, actually. I can first say it's V transpose times x, and the result is sigma. Result is then transformed by sigma, which is then transformed by U. Okay, and what is the point in writing this, right? Well, here's the really interesting part, right? Which is that if I take, so if I kind of draw a picture, okay, and I kind of think of this as Rn, right? And then we know that multiplying A or A acting on Rn as a linear transformation transforms it into Rm. Okay. And what we just saw, for example, is like over here, that A times V is equal to U times sigma. So for example, if I have V1 is a unit vector, right? So it's on the unit sphere. And remember, the V's are orthogonal. So V2 is going to be somewhere here, right? That's going to be transformed into something like, depending upon A, this could be sigma 1 U1. And suppose this is the unit square, then it could be magnified, or it could be the norm could be actually smaller than 1. And then maybe sigma 2 U2 is something like this, right? That's what this says, right? But based on the SVD, I can actually decompose it further, right? I can say that A times x is essentially three transformations: V transpose times x, sigma times the result, times U times the result. So I can write this as that first, there's an action of V transpose. And what does that give us? Where is V1 mapped onto? Let me try to maybe use a different color. Well, before I do that, so when I'm asking what is V transpose times V, V1, and V transpose times V2? Because I'm wanted to see the image of the vector V1 and of V2. Sorry, I think I wrote U2 over here. Change that. So let's look at it, right? Let EI be the ith column of the identity. So E1 is 1 0 0 0, and EI is it's the ith column of the identity. So just 1 1 in the ith place, and zeros otherwise. Okay, so EI is the ith column of identity. Let me write that. EI is ith column of the identity matrix. So what is V times EI? Well, it just picks out the ith column. Okay, if I now multiply both sides by V transpose, I get V transpose V EI is equal to V transpose VI. But V transpose V is identity. So EI is equal to V transpose VI. Okay. So what that means is that V transpose V1 is E1. And this is E2. Which means that this is E1. It's basically along the axis on the unit sphere. This is E2. This is on the unit sphere. And what this map V transpose is doing is that V1 is mapped onto E1 and V2 is mapped onto E2. Okay, so that's the first part of the linear transform. The second part is, remember, U sigma V transpose. So the second part is sigma. Okay, so if I do sigma, well, what is sigma? It's just actually stretching each dimension. Okay, so E1 is going to be mapped onto sigma 1 E1. Okay, so the unit sphere is somewhere over here. Okay, and sigma 2, so E2 is mapped to sigma 2 E2. Hey, is that clear? Because sigma is a diagonal matrix, right? So sigma times E1 is equal to sigma 1 times E1, and the matrix sigma times E2 is equal to sigma 2 times E2. So it's just stretching of the axis. And then finally, we have the third part, which is U, and this is the action of U. Okay, and remember that U times EI, what is that? It's just picking up the ith column of the matrix U. So it's just UI. So this is what is happening. Let me get back the same color. So E1 gets mapped to sigma 1 E1. E2 gets mapped to sigma 2 E2. Okay, and then sigma 1 E1 gets mapped to sigma 1 U1. And sigma 2 E2 gets mapped to sigma 2 U2. Okay, so again, like a very, really interesting way to think about a linear transform, right? That you think of just a linear transform of mapping things, vectors onto other vectors, but you can actually break it down to where it, and one thing I did not mention explicitly, that this is Rn and this is Rm. Okay. And then I think Hormuz had asked me, okay, what is the point of carrying around these vectors UR plus 1 through UM? So again, a very beautiful characterization of the singular value decomposition is the following, right? So if matrix A, I haven't spoken about rank so far, but if matrix A has rank R, okay, and R has to be less than equal to minimum of Mn. And if M is greater than or equal to N, it means that R is less than or equal to N. So R is the rank of the matrix, and that's exactly equal to the number of non-zero singular values. That's really the almost numerically the best way to determine the rank of a matrix is to actually do an SVD. Okay, so let me write it out. This means that sigma 1 is greater than or equal to sigma 2 is greater than or equal to sigma r, and this is greater than 0. And what that means is that sigma r plus 1 equals sigma r plus 2 to sigma n equals 0. Okay? And then if I think about A, my matrix A, then I have A is Rn to Rm. This is, it maps V1, as we saw, to U1 sigma 1, V2 to U2 sigma 2, VR to UR sigma R, and VR plus 1, it actually maps to 0 because the rank is R. And similarly, VR plus or Vn is mapped to 0. Note that R may be equal to n, in which case there is no vector VR plus 1 through Vn. Okay? And then we have A transpose, which maps Rm to Rn. And I have that U1 is mapped to V1 sigma 1. U2 is mapped to V2 sigma 2. UR is mapped to VR sigma R. And then UR plus 1 is mapped to 0. And we are assuming that M is greater than or equal to N for now. So UR plus 1 through UM is mapped to 0. So the beautiful thing that the SVD does, okay, it provides a very special, sorry, my R is a little funky. It provides an orthogonal basis for the 4 fundamental subspaces of A. And what are the 4 fundamental subspaces? And some of you might have seen this in your linear algebra class. It's the column space of the matrix A, which is often denoted as the range space of A. The other is the row space of the matrix. And you probably saw, right, that the row rank in your undergraduate linear algebra course, that the row rank is the same as the column rank, right? And it just falls out of the SVD, right? So it's I can write the range space of A transpose. Then I have the null space, which is null space of A. I have null space of A transpose is equal to null space of A transpose. I don't need to get all fancy over here, so. Okay. And this is the basis of this space is U1, U2 through UR. The basis of this is V1, V2 through VR. But since the row space and the column space have the same dimension, and that's the same as the rank of the matrix, there are R vectors in any orthogonal basis. And then the null space is VR plus 1, VR plus 2 through Vn. And then the null space of A transpose is UR plus 1, UR plus 2. And since we are assuming that M is greater than or equal to N, I have UM. Okay, so like I said, the SVD is a really important matrix decomposition, and many times it's known as the Rolls-Royce. Okay, but it's also incredibly useful computationally. So that's why it is called as the Swiss Army knife. Very useful in many different applications, including in machine learning. Okay, and let me give one more property of the SVD, and then we'll move on to regression. Okay, and this again, like a very important property of an SVD. So if A belongs to is an M by N matrix, we've seen that the truncated or thin SVD. Okay, where and let's actually consider the truncated SVD, right? Which is, let K be any number, okay, for any K where K belongs to min Mn. Okay, let me write AK, the truncated SVD, as A is equal to UK sigma K VK transpose. Okay, and UK is R M by K. It's orthogonal. Sorry, UK transpose UK is identity. Okay, sigma K is K by K. Okay, and VK is K by N. VK transpose VK. So all I've done is the following, right? So all I've done is I'm saying that you can take any K, okay? And I can basically just take the first K columns or the first K left singular vectors, the first K singular values. And crucial over here is that the singular values are decreasing. And then I can take the first K rows of V transpose. Remember that this will again give an M by N matrix, but it has rank K by construction, as long as K is less than R. Okay, so I should say that. Okay. And here's the very important property. Okay. Suppose I fix K. So you can actually take, for example, K equal to 1 or K equal to 2. Okay. Rank of AK is K. And the SVD has the property. And remember, AK is the, sorry, AK is this matrix. So AK is clearly of rank K. It's an M by N matrix. Okay, but it's this special matrix, which is UK sigma K VK transpose. And the theorem is that among all rank K approximations, of A, AK is the best. And what does it mean to be the best? It means that if I look at the matrix A, remember my given matrix is A. If I look at all matrices B, which are rank K, so B is of rank K, And if I try to take the minimizer among all rank K matrices, so argmin, this is equal to AK. And this is true in the 2 norm, and similarly, it is true in the Frobenius norm. Okay, and it is true for all K. Okay, so which means that, and remember that AK is equal to UK sigma K VK transpose. Okay, so with that, I kind of conclude talking about the singular value decomposition, but it's really an amazing decomposition among all matrix decompositions that exist. Any questions so far? I'm now going to move on to regression and
So
seeing how the SVD can be, how the SVD helps us over there.
I have a question, if I may. So
Please.
those sigma values, like the singular values, like sigma 1 to sigma n. Okay, so when we do the K rank, so you mentioned that these are like kind of sorted. So the sigma
Yes.
1 is the greatest one and the biggest, and then all the way to sigma n. So when we
Yes.
do the K rank thing, let's say we do K equals 2. So
Yes.
sigma 1 and sigma 2 are the exact value of the full decomposition.
Exactly. So they are exactly this sigma 1
Mhm.
and this sigma 2. So basically, it's saying that I can take this decomposition, which is the full SVD, and I can basically just take any K left singular vectors, any K, the top K singular values, and the top K right singular vectors. And if I multiply them out, UK, sigma K, VK transpose, then among all possible Rankine approximations of A, this is the closest to A.
That's pretty powerful.
Yes, it's a beautiful property, and somewhat surprising if you think about it. Really, it's kind of like if I just look at this particular problem over here, and I think about trying to solve it, this particular problem, it's actually not clear that there is a closed rank solution. This problem is not really even convex because rank is not a kind of convex function, but it's just kind of the wonders of single value decomposition that have this nested property. It's basically a nested property.
Yeah. It's just like we can some sort of partition the matrix that you want and then give you that. Yeah, that's
Yeah,
very beautiful.
yeah. So I mean, I can't stop gushing about the SVD, but it's really kind of a remarkable decomposition. And it actually helps us in, like I said, it helps us in interpretation of many things. It helps us in also computationally. So let's talk a little bit about, let's go back to our regression problem. And let's give an example of one way it can help us in interpreting regression. And then next lecture, I'll talk a little bit about regularization, which actually is a very important component of linear regression, right? And we'll see how it again helps us in interpreting things like ridge regression, okay? So remember, regression is the problem. Let me go back now to where you have this training data, xi, yi, and based on that, I can form the vector y. I have the matrix X transpose, which is X is 1, x1, 1, x2, 1. We were assuming that we have capital N training data. So remember, we have xi, yi, I is between 1 and capital N. Xi belongs to R D, and yi belongs to R. So we can form the matrix X, and the regression problem is that we want to find coefficients W, or a linear model, so that we find the best fit among all W's to the training data. Okay? And in the very first lecture on regression, we saw that, this least squares objective has a solution. Which is that, and we derived it using two different ways, one geometric and one looking at gradients. XX transpose times W star, that's the optimal, that's the minimizer of this, is equal to X times Y. So W star is the solution, and if W star, if the matrix XX transpose is non-singular, then I have XX transpose inverse times XY. Okay. And now, so remember that, I have XI, YI, right, from 1 to N. And if I now think about what is X transpose W star? It is a prediction, right? It's the prediction of, so that's equal to Y hat, right? Because W star is now my coefficients, and X transpose W star is the prediction. So I can think of it as an approximation to yi, which is the actual value. But let's see what happens, right? If I got that W star is this quantity. And so I have Y hat is X transpose inverse times XY. Okay, so this is the prediction on training data. Training data set. Okay, so this is the prediction on the training data set. Let's see what this actually means, right? And we'll see that the SVD will actually give you a really good way of interpreting what the solution of regression is, least squares regression, okay? So let X transpose equal to U sigma V transpose. I'm going to drop the hats, okay? Be the reduced SVD of X transpose. Okay, what does that mean? Let me look at X. So if I look over here, here is my solution to the least squares problem. It's XX transpose inverse times X transpose X. So let's use the SVD to expand these quantities, to look more deeper into these quantities, right? So I have XX transpose, then I have XX transpose inverse, and then I have X transpose, X transpose inverse times X. Okay, those are the different matrices that come up from here. And let's use the SVD to analyze this, okay? So what is XX transpose? Is equal to V sigma. Remember, sigma is square U transpose times U sigma V transpose. Okay, remember that I'm actually looking at this. So just one subtlety, that I'm assuming that U sigma V transpose is the SVD of X transpose. Okay, just to kind of keep the notation the same as before. Okay, but I think I used X transpose as the, coefficients matrix over here. So I'm taking the SVD of this matrix. Okay. So now U transpose U is the identity matrix. Remember, U is a column orthogonal matrix. And so I have V sigma square V transpose. And now I have XX transpose inverse is V sigma square V transpose from here, right? So I need to take the inverse of this matrix. Okay, and remember that the inverse of a product is the product of the inverses multiplied in opposite order. So it becomes V transpose inverse sigma square inverse V inverse. Okay, I'm in the case where, remember, V is a square matrix. So this is equal to V sigma minus 2 V transpose. Okay, because I have that V inverse is equal to V transpose. Okay, right? V inverse V equal to I, V transpose V equal to I, so V inverse is equal to V transpose. So I actually have a nice formula for inverse of XX transpose. Okay, now if I plug that in, right, I can plug it over here. And then I have X on either side, X on this side, X transpose on this side. So let's put it all together, right? So I have X transpose is U sigma V transpose. Then I have XX transpose inverse is V sigma minus 2 V transpose from above. Same thing over here. And then I have V sigma U transpose. Okay, so it looks a little tedious, right? But look at what happens. V transpose V is the identity. V transpose V is the identity. So I get U sigma minus 2 sigma U transpose. Okay, this is the identity because sigma is a diagonal matrix. So sigma times sigma minus 2 times sigma is identity. And look at that, it becomes U transpose. Is UU transpose the identity? No.
Necessarily.
Because, exactly, not necessarily. Because, in our case, X is a rectangular matrix. And when we looked at the thin or the reduced SVD, U is also a rectangular matrix, right? So in particular, remember that, what is the dimension of X? X is R D plus 1 by N. Okay. And then U is, U1, U2 through U D plus 1. Okay, so U transpose U is the identity, but UU transpose is not the identity. And if you think about what UU transpose is, right, UU transpose is U1, U2 to UD plus 1 times U1 transpose, U2 transpose, UD plus 1 transpose. It's actually equal to U1, U1 transpose plus U2, U2 transpose plus UD plus 1, UD plus 1 transpose. Okay. And so you can look at this and you realize that UU transpose is essentially the orthogonal projector onto the range space of X transpose. So that's all what linear regression is doing. Okay, what linear regression is doing is basically taking this vector y and then doing this transformation, UU transpose y. So basically taking, so if I have, the range space of, this is the range space of X transpose. Okay, is taking this vector y, which may not live in this range space, which means that the training data, when we do linear regression on the training data, we won't get a zero training set, a zero error on the training set. It's basically kind of dropping a perpendicular onto this, and this is UU transpose X. Okay, and you can again see that this is U1 transpose plus U2 transpose plus UD plus 1 transpose times Y, right? And I can write this as U1 transpose Y plus U2 transpose Y. And remember, all these UIs are perpendicular to each other. So it's basically like projecting onto each of the vectors, right? And which is equivalent to projecting onto the column space of, or range space of X transpose. Okay, so we've seen now, and that's actually how we did the if you remember, that's how we exactly did the geometric derivation of least squares regression. And now, algebraically, we've kind of also verified. So sometimes, like, beautiful part of doing work in this area is that you might actually have some formulae, but many times you might be able to, not always, might be able to give like a geometric intuition or interpretation behind what you're doing. And least squares regression is one case where it kind of comes very beautifully together. Okay, so that concludes this lecture. Any questions? So next time what we will do is we will look at the ways in which the current formulation we have of linear regression might be inadequate. And we will look at a couple of ways of regularizing so that our predictions actually become better. They don't overfit. And two popular ways are ridge regression and something called the lasso. So we look at these couple of different ways of doing regularization, and that'll bring us close to the end of looking at regression. After that, I will look at, a popular kind of collaborative filtering problem. We'll also give you a homework. So I think you can expect your first homework to come to you on, I think, next Monday. We'll assign the first homework. Any questions? If not, let's conclude, and I will see you all on Wednesday. Okay, thank you.
You.
Thank you.